Hello and welcome. In this video, we're going to discuss series voltage division. So in our first basic circuit, we saw that when there was only one single resistor in the circuit, all the voltage drop would drop across it. So if we placed a 5-volt battery, then we expected 5 volts to drop across that single resistance. And we still expect the same thing when we have multiple resistors, except for the entire voltage drop, 5 volts, would drop across both resistors in this case, or any resistors that we have in the circuit, which means that the voltage distributes across the total resistance. In this case, the total resistance, since these two are in series with each other, we have no choice but to go through both of those two. We can call those in series, so we'll add them together, and we'll say that our total resistance is R1 plus R2, and since they're both 100 ohm resistors there, we end up with a total resistance of 200. So we can measure the voltage drop across that. That's this right here. We measure the voltage drop across R1 here because we're measuring around that resistor, and that's going to pull out the voltage potential on either side there, and it's going to compare the positive side of the meter here to the negative side of the meter, and it says that there's 5 volts on this side and 2.5 volts on this side. And when they subtract those two, 5 minus 2.5 gives you 2.5. And so if we take this 2.5 volts, which is the voltage drop across R1, we can place that in a voltage ratio equation here. We can say that we have the voltage, VR1, and the voltage source. We can divide them. Right? 2.5 divided by 5 gives you 1/2, or 0.5. And if we multiply that by 100 to get our percentage equation out, we'll see that that is 50% of our voltage source. And we expect the same thing to happen across R2. 2.5 is left over, remaining in the circuit, so we expect to measure 2.5 volts on top. And since this is connected to ground at the bottom, we expect this bottom one to be 0 volts. So we should be able to measure 2.5 volts across R2 as well. We can focus this on our resistance ratio also. We can say, well, let's put R1, 100, on top, and our total resistance, RT, 200, on bottom. And that gives us the same equation, the same ratio of 1/2, or 0.5. And when we multiply that by our 100, we also get 50%. So we can represent the voltage division in this circuit using both the voltage itself compared to the source voltage, or the resistance that we're talking about compared to the total resistance in the circuit. And this is how we're going to predict some of these. Let's look at another one. This circuit's slightly different. We still have a 200 total resistance because we still have a series connection here of 50 ohms for the first one and 150 for the second one. So when we add those together, we end up with a total resistance of 200 still. And when we look at the voltage drop across R1, we can say that when measured, the voltage drop is 1.25. And that's the voltage that this first resistor consumed. Note that the smaller resistor consumes less voltage than the larger resistor. Right, so when we place that into our ratio equation here, we'll put our voltage, VR1, that's this voltage value right here. VR1 goes on top, 1.25 volts, 5 volts on bottom there. And when we calculate that out, we get a 1/4. And when we multiply that by 100, we end up with 25%. So 25% of the total 5 volts is dropped across R1. You can do that with the ratio equation for resistance also. We put R1 on top and RT on bottom, right? 50 ohms on top, that's our 50 ohm resistor, divided by 200 ohms, that's our total resistance that we calculated out. And we were given the exact same output. 25% of our total voltage will drop across that resistance. Now if we focus on R2, we can see the same thing. KVL, Kirchhoff's voltage law, it's stated up here. We'll just call that KVL. It says that no voltage is left behind. It says that by the end of the circuit here, this ground location, we're going to have 0 volts left. 5 volts at the top, 0 volts by the bottom. So if we lose 1.25 volts across the first resistor, we can say 5 minus 1.25 volts will equal the voltage drop, VR2, and the voltage drop across the second resistor. And that is going to be 3.75 volts. So we can kind of predict what that second resistor will consume in terms of voltage just based off of what we know about the first resistor. So that's how we got to the second one down here, VR2 divided by the source voltage. 3.75 divided by 5 gives us 3/4 of the total voltage drop, which gives us 75%. And note that the 25% here and the 75% here add up to 100. That's what we want for that. Same thing goes for our total resistance in this circuit. We can compare R2 on top to the total resistance on bottom. We'll get 150 for our R2 value there. divided by 200 gives us 3/4, right? Or 75%. And so both work. The voltage ratio and the resistance ratio will both get you the same percentage output for voltage drop. So we're going to use this to determine our voltage drop using the voltage divider equation. Let us know if you have any questions.